Take it away, sir.
Despite all the lies, I've been doing this kind of bumbling around for many years. I've known David 34, 35 years. How long have we known each other, David?
You came to Princeton after your, like, for postdoc, 90.
Yeah, but we knew, I knew you when I was a graduate student.
Oh, that's right.
Yeah, a long time ago. So I would say we've known each other since about 88, 87, something like that. So that is longer ago than probably almost all of the graduate students in the room. And the way this is set up, I cannot see what's going on in the room. All I can see is my slides.
I'll keep an eye on for you. But should I play with that some? Because we do have this camera.
I think it's Zoom. It only allows me, between Zoom and Microsoft, it only allows me to do so much. So let me tell you a little bit more about myself. I have done modeling and experimental work, a little bit of theory, but a bunch of modeling, a bunch of experimental work over all of these years. And one of the things
does that work? Can you see another screen now, which is a picture of the room?
Nope.
Okay,
all I can see is Microsoft.
Okay, well then I'm gonna not mess with this because it blocks up more of the screen.
Yeah. Don't worry about it. If they fall asleep, throw erasers at them.
Got it. And if I fall asleep,
I'll fly up there and kick you. I'll hear you snoring.
Got it.
So as I was about ready to say, one of the things that I've always tried to do is link the modeling with the experimental work. You can model things day and night, and if the models are wrong, no matter what you do with the models, they're still going to be wrong. You're not going to be able to have predictive results. And this is actually fairly important, as I'll show in a little bit. And so what I've been working on, besides experimental work, is how do we improve some of the predictive accuracy in plasma models? And I'll show you some of the things that have gone on. Oh, please let me go on. There. Okay. So when I was at Princeton, I put together this slide for the graduate students who were there about how some people view plasma processing or plasma physics in general. You put a bunch of raw material in, it's a black box, and out comes lots and lots of money. The reality is a little bit different. You put raw materials in, you're not quite sure what goes on, and out comes some money. And really, the desire here is to understand what's going on in that box better, so that instead of a few cents out, you actually get a lot of money out. A case in point, plasma processors that are used in the semiconductor industry, a single reactor might sell for $5 million. I believe David has something that he works with that is on the order of $100 million for patterning. Now, it's not quite processing, but it does use plasma physics. And that's a lot of money to throw at something. And you have on top of that, you're working in a clean room, and it's thousands and thousands of dollars per square or per cubic foot. And you're trying to make do by punching out a bunch of devices that are 5 cents a piece. So why should you care? What I have plotted here Can you see my cursor?
Yes.
Okay, so here is a rough product value and a rough number of devices produced. For a CPU in 2007, a couple $100 for a really nice CPU. Now they've gotten somewhat cheaper, but they're not that different. They were producing, I believe it was 300 million a year. And so if you were to take all of the sales and turn it into money you could spend on development, you can find that it's going to be very easy to be profitable. If you do the same thing with a medical device, where you might produce, where they might sell for $1,000 a piece, and you're producing maybe 10,000 of them or a few thousand, the ability to actually make money off of it becomes very difficult. So the green line here is a $10 million spent to develop it. Here's 100,000. So if I'm producing 10,000 at $1,000 a pop, I'm not making any money. Walmart for many years wanted to make RFID chips or tags for everything they sold. They wanted to be able to sell it for, use it for about 5 cents a piece. And it comes down to, this is the cost that it costs to have a checker. So how much does it cost in minimum wage? Can you replace that person on minimum wage with the RFID tag? 5 cents a tag is about the break-even point. You would have to have billions of them, tens of billions of them, and you'd have $10 million to do all of the development for it. And so it becomes very difficult to actually make this work. In order to make this have economic sense, one needs to really understand what it is you're doing so that you can kind of, from the get-go, come to a solution that makes sense for whatever process you're trying to develop. And here's what I said in words. You need to understand the fundamentals. So my way of viewing plasma science is that it has 3 subsystems. There's the plasma physics, which is here. There's some sort of surface physics / chemistry, and there's some sort of gas phase chemistry. And all of these interact. So for the plasmas, the electrons are going to run into the neutrals. They will break the neutrals up into smaller parts. You will have the sheath at the edge of the plasma. The ions will be accelerated across the sheath. They'll bombard the surface, driving up, giving energy to the surface, allowing reactions to occur. That's one way in which these things can interact. Surface kinetics, you can have processes occur on the surface, liberate gas that goes into the gas phase chemistry that interacts with the electrons, changing the electron energy distribution function. And so all of these things interact. There is a classic view of this, and this is the work of Coburn and Winters. I think they actually published the original work in 78, but this was a reprint in a book by Chapman. And what they did is they exposed silicon to xenon difluoride. It etches, chemically etches the silicon. They could measure the etch rate. It was about 7 angstroms a minute. Then they began to bombard the surface with an argon ion beam. You got an order of magnitude increase in the etch. They then pumped out the gas, and now you have just physical sputtering. You're basically doing billiard balls on the surface, knocking the surface atoms off. And you go back to that about 7 angstroms a minute of removal of surface material. And so you have this interaction between the chemistry and the energy that's brought to the surface, the bombardment due to the ions. And this happens in plasmas. And this allows you to do things that you cannot do in any other system. Plasmas have been known for 150 years. What have we learned? So in terms of understanding these interactions, kind of the simplest things that you can do is what's known as a global model. It is essentially 0 dimensions in velocity space, 0 dimensions in physical space. It's what the plasma system is doing kind of as a whole. You ignore the plasma sheath, you ignore the surface, well, not the surface kinetics, you ignore the variations across the system. And this allows you to get some sense of what's going on in the system. So this is work we did where we developed our own version of a global model. It assumes it's well mixed, and you can use it to study molecular wall interactions, among other things. And it has potential to save a bunch of time and resources. So this model looks essentially like this. You have a gas phase mass balance where you're producing the gas through some process. You're either pumping it in, pumping it out, breaking it up, or recombining it. You have surface processes. You have a power balance where you're depositing power into the system through your electrodes, either through the electric field or the magnetic field. That gets dumped into, there's a power absorbed, there's power lost to the electrons. The electrons and ions go to the wall. There's power lost to the pump. Electrons will get sucked out of the pump, ions will get sucked out of the pump. There's a couple of constraints, charge neutrality, and then there's the surface. What's happening at the surface sites are assumed, it's assumed that they are essentially steady state. And you put this all in a big blender that includes all of the chemical reactions you can think of. So here's some of the important gas phase reactions, plasma phase gas reactions that you might think of, where the electron is breaking up the gas that you have in the system. There's 29 of them. There's a bunch that we don't know. You have ion-ion recombination processes. You have detachment. You have associative collisional detachment. And there's a bunch you don't know. But we can kind of guess what these reaction rates might be. And in the right system, we can actually determine values for these. There's 2 major caveats. Not all the reactions have been studied. We don't know all of them. And it's assumed that all reactions have well-defined species temperatures. So here, for example, the electron energy distribution function is going to play a major role in how this, how this reaction occurs. Slow electrons will typically not do it, fast electrons will. So we put this together, we plotted out what we expected the neutral densities of different species might be in the system as a function of power that you put into the system. We were not the first people to do this. Goeckner did this a couple of years before us. We got the same answers that Goeckner did. or close to the same. Not surprising, we're using largely the same method. Well, how does this compare to experiment? We had been measuring all of these gas-phase chemistry densities for years and trying to model and trying to come up with reaction processes that would describe them. So here is the C2F4 density versus power. This is at a particular pressure in the system. And the green line is what we measure. It's on this side. The yellow line is what the model says. Notice that they go in two different directions. That's part one. Part two, this is 10 to the 20. The other one's 10 to the 19. So they go in the wrong directions and they're off by an order of magnitude. CF2 density, again, going in the wrong direction. Now, fortunately for us, the ion flux looks about right. The electron temperature is, well, it's in the right ballpark, but it's off some. Bottom line, though, is that the model is not sufficient to describe the processes that we were measuring. And we were very careful on how we did these experiments. So we were very certain about those measurements. The error bars on the experiments are about the size of the dots on there. If there are any questions, just yell. Otherwise, I feel like I'm talking to a box at home.
I know you still got us. Yeah, I think they're awake, Matt. Okay, you can hear me, right?
Yeah, I hear you.
Okay, no, we got this. So yes, your model, it sucks compared to the experiment. Got it, okay.
All right, so the bottom line, some of the model is corrected for some things, but it's not a real good match in all things. And by the way, these are really important. So does anybody know what happens to this C2F4 or CF2?
I do.
Now, I don't care about you.
I know. Okay, what's CF2, guys? Come on, somebody plasma guys. Why would you not care about making CF2 in a plasma? What is it going to do? Increase selectivity. I don't think.
And why is that?
Yeah, why?
What might CF2 become?
So we're using this to etch or deposit stuff.
Well, it's definitely going to deposit. You can use it to etch too if you do the right sort of thing.
Come on, I know a lot of you had 429. What's the kind of etching that's used today? It's called what kind of etching? Starts with an I. Inhibitor etching. And what's the inhibitor on the sidewall? Yes. Teflon, CF2.
Yeah,
Okay.
CF2N. It's a long chain of CF2N.
Yeah, Teflon. Okay.
And so this CF2, actually in our experiments, we were able to show that this C2F4, that there's a large fraction of it was unterminated. So you can have a stable molecule that's C2F4, where the carbon is a double bonded system. But you can also have an unterminated version of this, where the CF2 has recombined in the gas phase. We were able to measure that recombination rate. So both of them, the unterminated C2F4 and the CF2, will produce Teflon all over the place, or a Teflon-like material. It is not truly Teflon because it's not truly a polymer. And you're going to deposit this all over the place, including the sidewalls of a trench or a via that you're etching, or the sidewalls of your reactor. And eventually you've got to clean it off of the sidewalls of the reactor. Otherwise you peel off thin layers of Teflon. It's like Teflon tape that you use as a pipe dope, essentially. So you know the Teflon tape that you can get for screwing together two pipes for plumbing. It will look like that on the inside of your system. So this is an important gas here. And the fact that it is wrong is very important because it tells you the wrong thing when you're trying to model whether or not you're etching correctly. So we don't have the match that we really want. There are assumptions that fail here. One is that there is a temperature. What does it mean to have a temperature? Anybody know?
Shout it out, someone. All right, someone said Boltzmann distribution.
That's right. There's other versions that can define a temperature, but it means that it is well mixed. It's in thermal equilibrium. And the temperature is a measure of the width of the distribution. And the fact of the matter is, in most experimental plasmas, it is not as well mixed as one might want. And furthermore, the high energy part of the distribution, where all of the chemical reactions, all of the ionization, and everything else is going on, is just, we don't really know what it is. And so there's this imprecision that we have. We're assuming it's a Maxwellian distribution. It's likely not. So the next simplest model that we can look at is a fluid model. And here we used COMSOL, which is a widely available system, where we actually modeled an electron beam system that we built as a diagnostic, a chemical diagnostic. So we would pull electrons out of a little hole with a plasma bottle. We'd pull electrons out at a well-known energy, and we were able to actually measure electron excitation cross sections, and from that tell what was in the gas phase. So we did this model to study what was going on in the system. And we were able to plot out what the gaps should look like. And it was close, but again, it got back to the point of, with this fluid model, you're making assumptions about what's going on in the electron source. If I have a bunch of high energy electrons in here, it's going to change the flux of the electrons that come out of the gap because of the potential structure. Things become even more interesting. We've done a lot of work in pulse plasmas, where you're turning the plasma on and off at the kilohertz range. You might be driving it at the megahertz frequency, where you have a voltage or something at the megahertz frequency, and then you turn it off and leave it off for a fraction of a second and turn it back on, and what happens? You can have organic precursors. There's a huge amount of potential work that can be done here for biomedical applications. The list of organic precursors that you could put into a plasma is pages and pages long. Atmospheric pressure plasmas is something that we're working on quite a bit in my lab. What happens in those sorts of systems? Can you change how that system operates by changing how the plasma is set up? Is it really in thermal equilibrium? That's usually what people do for some of these atmospheric discharges. So here is an example of a pulse discharge, where we're pulsing it at 1 kilohertz. It's a square wave pulse. The power is 13.56 megahertz. And when we turn the plasma back on, there's an electrode the system looks like this. There's a powered top electrode, there's a plasma, there's a lower chuck where you might put a wafer. When we turn it on, we see a bright glow on one side. So that would sit right about here in the system. And then we see a glow in the middle. The bright glow extends across the whole regime and it comes down. It looks like something's happening here. It's a little bit hard to tell with just a series of pictures. So what are we going to do? I hope this works. It worked earlier. Here's a movie of it. This is actually experimental data.
Ooh, cool.
Anybody notice that bounce of the glow?
Mhm.
What is causing that? You have waves propagating up and down the system. So here we were running in a CF4 oxygen argon mixture at 45, 45, 10. If I do this same experiment, oops, didn't go to the next slide, it replayed it. Come on, go to the next slide. Okay, just CF4. Notice how different that is? We didn't change anything else other than the gas phase chemistry. This one also pulses in the same way, but it doesn't have the reaction that was occurring on the side. I think I know what that was, but it's hard to tell for sure. So all we did was change the gas phase chemistry, and we got a very, very different reaction. And CF4 or CF4O2 argon, those are standard systems to run in the semiconductor industry. Those flow rates, those mixtures, that pulse rate, that's all common. And if you're getting this big of a difference going between gas mixtures, how can you ever be sure that you're going to get the same result twice? How can you understand what it is that you're doing? Of course, it wants to flow again. No. So we can look at it for a bunch of different things, and this is just normalized intensity as a function of time after the pulse is turned back on. Argon is purple. You see it's kind of a slow rise. Nitrogen is intermediate. Oxygen comes on very fast and then goes down to steady state. Steady state is about here for the glow. You get very different responses depending on what your feed gas is. What does this mean? Does anybody want to tell me what this means? Those of you in plasma should have some. What does the emission mean?
I mean,
Are they still there, David?
I'm here, you're looking for, I mean, the emission is proportional to the number of those atoms that you have. Is that what
Yep.
you mean?
What else does it depend on?
Well, you have to excite them, so you have to have enough electrons to be able to make these transitions at those energies.
Did the students answer, or is that you?
That's me. I don't know, they're all asleep. No, they're not. Okay. You do
Oh,
that.
they're all great. We'll hit the bars in a bit.
Okay, okay,
Okay, so here's what the emission is.
there we go.
There's an electron energy distribution function. It's some sort of distribution function. There's a cross section that's velocity dependent, and it's an integration over all of the velocity at that particular point in space. And so your emission can be time and location dependent because the velocity distribution function is time and location dependent. It's also dependent upon the species in the system. Remember, if I change the species in the system, I'm going to change the collisions, which is going to change the distribution function. The cross-section will be species dependent. Other data, reactor seasoning is important. Reactor temperature is important. Why might reactor temperature be important?
Come on, guys. Why do you care how hot the walls are? Walls are the same temperature as what? And ions because of the same temperature as the
So
gas.
what happens if I take a vacuum chamber and I dip it in liquid nitrogen? I've got a closed up vacuum chamber, I dip it in liquid nitrogen. What's going to happen to the pressure inside the vacuum chamber?
Oh, good. Lots of people are pointing down. All right.
Okay. What happens if I now raise the temperature to 200 degrees?
Goes up.
Why?
Ideal gas law. I'm sure someone said that.
Ideal gas law is one reason.
Okay.
What else happens?
Think of it, what happens with water vapor in your chamber if you go above or below 100. Yeah, outgassing comes off the wall. They said that.
Outgassing. So reactor chamber becomes very important because you can push off water off the walls. You can push lots of things off the walls, but at the very least, you can push water off the walls. And we did studies, Joe Checky did studies, if you don't know who Joe Checky is, years ago where we looked at the water coming off the walls and how this affects distribution functions and potentials. And it has a huge effect, and it's just little bits of water, okay? And so all of this that we're seeing, those last few slides, you're seeing these huge differences because the distribution function is changing because of this and this. The chemistries that we might want to use. This is EDOT, the precursor for making something called PDOT. It is a polymer film that is very conductive, used in flexible electronics. We were trying to figure out if we could break it up in such a way that we could make plasma polymerized polymer or conductive polymers. So we did lots and lots of studies, and I'm going to show those to you in a few minutes. And you want to guess what we found? I will answer in a minute. Anybody want to guess? Did it work or not?
Let's see, you haven't founded the company and aren't driving a Ferrari and jetting around, and you're still talking to us on a day job. So I'd say no.
That's not the right way to think about it. Okay, so we use an FTIR to measure the gas phase densities. And actually, these are the CC band stretch. So there's a double bond stretch that we're looking at. So there's an anti-symmetric and a symmetric. It's a measure of how many of the bonds are in there. And so what we're finding is that we're breaking one of these double bonds, if not both of them. The other place that we would really like to break it is the carbon sulfur bond that sits right here. And what we find is that it's essentially constant no matter what we do with the plasma. The problem is that in order to make a conductive PDOT, we actually have to break the carbon sulfur bond. And we cannot tune the plasma in such a way to get it so that we preferentially break that. The pi bond for the carbon-carbon double bond is much weaker than the carbon-sulfur bond. And you need the carbon-sulfur bond to break to make p dot. So it is not conductive. So we get back to this dissociation. Again, there's a cross section, there's a distribution function of the electrons. Reactor seasoning again, reactor temperature, same takeaway. So what is so fundamental? Those of you who suffered through my class this spring know that the Boltzmann equation is the critical equation here.
And you folks in 527, right? All right, okay.
Yeah, this equation is the critical equation where the EDF or the distribution function is really important. For you can have a Poisson-Boltzmann model for argon discharge. Here you have the model for the electrons, the model for the argon ions, and the model for the argon. You add in Boltzmann's equation or Poisson's equation to determine what the local electric field, and all of this is trivial. I'm shaking my head no. We still have boundary conditions, but potentially you can model this with some sort of fluid model. Well, there's another problem. This is the work of Mark Goeckner. For those of you who don't know who Mark Goeckner is, he is probably the preeminent plasma modeler for low temperature plasmas. And has been for 20 or 30 years. David, is that a correct statement about Mark?
Absolutely. Mark was here as a professor for most of my career. We were friends. Our friends, worked together. He moved. He was a dean, and then he's at University of Michigan now. They gave a big giant plasma science center. But yes, if anyone in the world can model a plasma, Mark can.
Yes. And so here's one of the fundamental problems. If you're trying to look at the electromagnetic fields, the time steps that you need to use to get the fields right are 10 to the minus 12 seconds. If you're trying to model surface chemistry, 10 to the minus 4, 10 to the minus 2. So there's this huge discontinuity in what happens in the plasma models. And you have to break them up. You have to simplify things in such a way that you can link them up. If I'm trying to study what's going on the surface and I have to have 10 to the 8 steps for every time I make a step in the surface chemistry, I will never get it done. And so these differences in timescales have huge implications on how you write code and what you have to do to get the code to even come close to being right. Another thing that's important here is the collisions are not really all that well understood. Those of you, again, who had my plasma class this spring will know what this looks like, and it's not a bit of algebra, it's a lot of algebra. This is the collision between particles of type alpha and beta, and it is a 5-dimensional integral. I'm integrating over a solid angle and the velocity of the beta particles. This is the distribution function of the alpha particles. That's the beta. These are post collisions. These are pre. And you can think of this as the collision cross section. It's related to the collision cross section. If you want to calculate these collisions in 3 space, that's an 11-dimensional integral. It's very expensive to calculate. And so we've done work where we've cut it down to 5 to try and do a better job. And there's other ways to get it. I'll show you a little bit later, but it's very expensive. Last but not least, let's go back to the why is it so complex? It's the interactions. We have a whole bunch of unknowns. We have time and location dependent electron distribution functions. Calculations are computationally intensive. The EDF is very critical to many processes. There's species dependence on what the EDF is. We don't know a lot of cross sections. There's a lot of species that might be in the discharge. We don't know what they are. Oh, there's this minor problem. Does anybody know what a secondary electron is?
Sure do. They're nodding their head yes.
Somebody want to explain what it is?
Come on, Zach, you can do it. I saw you nod your head yes. Right. I don't know if you heard that. He said it's the electrons that come off from the surface of your vessel.
Yes. So what happens is you can get this from a number of processes, but say you have an ion coming to the surface that has 10 eV of energy just as it hits the surface. About an angstrom above the surface, you'll get an Auger electron that will jump across and neutralize the ion. Occasionally, you will get a second one that comes at the same time. And there are other ways that this can happen. But this second one has no place to go. It is not neutralizing the ion. It now is in the sheath and goes flying out away from the system. And so you're producing all of these secondary electrons. The study of secondary electrons is from the 50s and 60s, and they probably get it right down to 1/10 of an eV, 100th of an eV. Well, that's great, but a plasma also has something else at its edge, and that's the sheath. That means I now have an additional electric field. So here is my surface. Can you see my hand?
Yeah, small, but yeah.
There's the ion. There's this huge electric field between the two. If I impose on it another electric field, now what am I doing inside my surface? I'm drawing more electrons to the surface to try and balance that out. And so if you have a sheath present, there is reason to believe that the secondary electron coefficient changes because of the sheath. That has not been proven to my knowledge. We tried, we couldn't get the experiments to work. But Gary Eden, who was at Illinois, what?
He still is, just because you go emeritus, he still has a.
Oh, he's emeritus, okay. He did lots of work which showed that the secondary electron coefficient changes with that electric field. And so that's an unknown. We don't know what's going on. There's also this problem of how plasma science has been focused, at least for the low temperature plasma science. A lot of it has been focused on what can we do, not why it works. And this was possible because of the economics. There was so much money there that you could just throw money at the problem and get people to turn knobs until it worked. Now it's a little bit more elegant than somebody turning knobs. There was designed experiments to find regimes that work. But people spent a lot of hours trying to figure out what would make this work and that work. And we're down to 3 and 4 nanometer scale lengths. Could not do that any other way. There's a lot we don't understand. So I'm going to start asking the question, what can we do in order to truly understand this so that we can use plasmas other places where there is potential use to improve the human condition, improve how the world works. But we don't have this economic ability to just throw money at the problem. Medical is an example. So here is my suggested solution. One, we need to have a large collection of electron impact cross sections, and it needs to be coordinated in such a way. When I first put this talk together, there was a whole bunch of them. That's been done. I managed to con a bunch of people into putting this together, and we have it. You notice they even were nice enough to put my name in the paper.
Is that in LX cap as well now?
What?
Is that in LX cap, the cross section binder function?
You're going to have to say that again.
Can you get to this database with the program LXCAT?
So this is, you get the date to this database through Quantumol.
Okay.
And I believe that it's available in the journal, but there are some parts that you probably want to go to them to get it. But it is a database. This was started not unlike there's the atmospheric science people to study pollutions put together a database like this that we use all the time to get absorption cross sections for our IR measurements. So high trans is the atmospheric version of it. Step 2, we need to optimize computer simulations, and I'll come back to this in a minute. Step 3, now that we understand what the collisions are like in the gas phase and understand what's going on with the EDS better, we can now look at just the surface processes by themselves. If we know the other two really well, we can't do this before that point. Otherwise, it'll get lost in the unknowns for the other ones. So going back to step 2. So trying to understand what the EEDS are is really tough. And this is the fundamental problem. So what I have plotted here is, well, there should be a log of the distribution function on the energy scale. So here's a semi-log plot of the log of the EDF versus energy. And if it's a Maxwellian, it's a straight line. The ionization cross-section is here. Now, if I'm deep into the tail, if there's a slight move up in the tail, I'm going to get a lot more ionizations than if there's a slight dip down. So what happens deep into the tail above 10 eV is going to be critical to what goes on in terms of the ionization events. And remember, our temperature is 3 to 5 eV. So you're several TE out. You're several standard deviations out from the center of the distribution. So we need to model these accurately deep into the tail. And this shows up here and here. And we've come up with two different ones. One is a deterministic, where we're actually integrating the collision kernel, and the other is stochastic. You can think of that as Monte Carlo. How many people know what Monte Carlo is?
Oh, half the room raised their hands. We got a lot of neutron people here, you know. Okay.
Okay, so Monte Carlo, the city slash town where they gamble, Monte Carlo is effectively rolling the dice. You're looking at random processes. And Monte Carlo in this case is random collision events. And there's a certain amount of an art to it. So there's, in addition to the original version of Monte Carlo, which was done by Bird, which is known as direct simulation Monte Carlo. What Bird did is he put a bunch of particles in phase space, and this is just the velocity part of it, and shaped the distribution. Each of these little dots might correspond to 10 to the 8 or 10 to the 10 electrons or something like that. And each of them corresponds to the same number of electrons. So when I multiply the weight times the number of particles in my Monte Carlo, I'm going to get the probability distribution function, or the EEDF that you would know it as. Renshaw and Wagner came along and said, well, that's not the best way to do it. We're going to have different weights for all of the particles. So for the ones out at the edge, they're going to only count for 10 to the 6 electrons. And the ones in the center might be 10 to the 10 or something like that. And so now when you multiply it, you get the distribution function again. But notice what I have. I have a lot of particles out here. So my statistics are better. So there are some problems with Renshaw and Wagner's work. And so people tend to still use just the work of Bird and the standard Monte Carlo. We wanted to understand what's going out into detail. We actually wanted to know way out here. You probably don't need to know this. This is the reduction scheme.
Yeah, your host is standing up.
My host is standing up.
That's me.
That means we're about done.
Yeah.
Okay, so we were trying to measure it. We had different group formation techniques, and we're grouping particles. So with stochastic weighted particle method, you break up the particles when you have collisions, and you have to recombine them. Renshaw and Wagner they conserved energy, they conserved energy, and what was the other one? We conserve heat flux. So we actually conserve up to the third moment of the distribution. So this is the new stuff on this line. This is what Renshaw and Wagner did. And you notice we're getting to the correct answer a lot faster than theirs did. And so we have a considerably faster scheme to get deep into the tail. So if we have a temperature of 1, we can go 4 times the temperature out, and we're accurate. And so now we have a methodology to look deep into the tail of the distribution function. And at this point, we're trying to work with folks at Sandia to implement this on some of their code, with the eventual hope of putting it into simulations that we can use to actually model plasmas in a better way and understand what the distribution functions are doing better. So David, I got to the questions, and
Okay.
I've got a whole bunch of places.
And, a third of the people here do plasma. So, okay. Come on, let's get one good question. Stand here all day. Yes.
Sorry, I didn't do plasma, but I have a question. So are any of your results, the experimental results, sensitive to the initial condition or initial experimental setup. Take your CF2 oxygen and argon mixture experiment, for example. It seems that you have a one-time measurement, and I'm just curious about if you have a little tiny difference in your initial, let's say, composition in your mixture. Does the result varies a lot in terms of time?
So you're talking about the movies.
Yeah.
So I'm going to, let's go back to the movie quick, if I can get it to go. This movie, first of all, we took this time sequence in random order. The other thing that's important here is this was 30 hours worth of data collection. So if there's variations that are due to variations in the gas mixture, it should wash out because we took the time sequence in random order. And the other thing is that each of those pictures that are hidden in that file, 45 minutes of runtime. So short-term variations are not affecting us. Long-term variations are not affecting us. We were measuring the voltage and the current going to the powered electrode. The changes were a couple percent. Some of the runs we had were 3 days, and it was a couple percent over 3 days. We did not start taking this data until after the system had been running for an hour or two. It was stable.
Thank you.
Sure.
Any other questions?
Hey,
Has this new database improved the results of the initial CF4 modeling at all? Or is this, I don't know if they're connected or not.
David, you're going to have to repeat that. I can't.
sure, Charlie, it's pretty far back, but the new database that you worked on getting everyone put together, if you apply that back to your first models, would it improve it?
So they're in a process of writing a new paper, and I was going to be part of that new paper and do exactly that, but I have not had the free time, and so I backed out of helping. But that is kind of on the list of things I wouldn't mind doing, but I just haven't had time. All of this work trying to get the EEDFs deep into the tail, wherever it went.
Yeah. No.
Those pictures, that's a couple of years worth of work right there.
Yeah, and I'll tell you that's key. And if people are in my 5.7 class tomorrow, we're going to talk about exactly this type of thing, because all those reactions are up at those high energies, the electrons, and what little variations there make huge differences in what you get. So Matt, very timely lecture. And very good, and I think he actually kept them awake, and some of even the non-plasma people interested, so that's great. So everyone, let's give Matt a big round of applause. Okay?
Thank you all, and perhaps I'll make it back up to Illinois at some point. And
You're always welcome, Matt. You're always welcome.